roughly 252 million years ago. Heat shimmered over a wounded Pangea, while ash-dark rivers crossed nearly empty floodplains. The dinosaurs did not conquer a thriving world. Their distant ancestors entered landscapes where older ecological orders had already collapsed. This was not yet an age of dinosaur giants, but a long recovery dominated by survivors, experiments, and relentless instability. How did the first dinosaurs claw their way up from the deadliest catastrophe in Earth's history at all? The answer begins with creatures that survived the graveyard, because catastrophe opened ecological space long before dinosaurs learned to exploit it. Across the supercontinent, rivers wandered through open ground where vegetation was sparse, patchy, and vulnerable to every climatic swing. The Great Dying had erased countless relationships between predators, herbivores, plants, soils, and microbes, leaving recovery with no simple blueprint. Fossil evidence links that catastrophe to the Siberian traps, whose immense volcanism helped push Earth systems beyond familiar limits. Survival therefore favored flexibility, bodies that tolerated stress, diets that found scarce food, and behaviors that worked in simplified communities. A devastated ecosystem is not empty, however. It is crowded with opportunities created by every vanished competitor and broken food chain. Small plants returned along waterways first, stabilizing sediment and creating pockets where insects, amphibians, and land vertebrates could feed. Those pockets became biological islands, each one testing which survivors could reproduce quickly enough to endure another season of uncertainty. Recovery was measured not by dramatic victories, but by ordinary acts repeated millions of times: feeding, nesting, migrating, and surviving. From these repetitive struggles, new communities slowly assembled, and the first shape of the Triassic world began emerging from collapse. Yet the creatures rebuilding this world were not preparing a kingdom for dinosaurs. They were fighting simply to keep ecosystems functioning. Among the most successful land survivors were dicynodont relatives, sturdy plant eaters whose persistence made them symbols of early Triassic resilience. Lystrosaurus is especially famous because its fossils appear across large parts of Pangea, revealing how widely some survivors could spread. Its success did not mean the planet had healed. Dominance by a few hardy forms can signal an ecosystem still deeply simplified. Where diverse communities once divided resources among many specialists, recovery landscapes often rewarded generalists capable of enduring heat, drought, and scarcity. Burrows may have offered refuge from punishing surface conditions, turning underground shelter into one quiet advantage during ecological recovery. Above ground, every patch of vegetation mattered, because herbivores converted returning plants into energy that predators could finally exploit. This rebuilding happened from the bottom upward. Soils, plants, small prey, larger herbivores, and only then increasingly complex predator networks. Some lineages vanished despite surviving the initial extinction, a reminder that surviving catastrophe and succeeding afterward are completely different challenges. Natural selection was working within a damaged world, favoring traits useful for instability rather than traits perfected for vanished Permian ecosystems. Rivers became migration corridors, carrying animals between temporary wetlands while seasonal floods redistributed nutrients across otherwise dry interiors. Along those corridors, amphibians and reptiles encountered one another repeatedly, creating competition that could reshape feeding strategies and body plans. Predators followed concentrations of prey, so the geography of survival became the geography of hunting, ambush, escape, and reproduction. Each successful generation added complexity, yet the food webs remained vulnerable because losing one abundant species could still destabilize many others. That fragility explains why the Triassic recovery feels less like a steady climb and more like repeated rebuilding after repeated setbacks. The survivors had reopened the basic machinery of life, but climate would decide how quickly that machinery could become diverse again. Pangea gathered most continental land into one vast supercontinent, creating interiors far from oceans that could become intensely seasonal and dry. Coasts and river basins offered relief, yet inland habitats could swing between scarcity and sudden floods, challenging every recovering population. Heat influenced where animals could forage, when plants could grow, and how much water remained available through difficult seasons. or cold-blooded animals, temperature-shaped activity directly, turning shade, water, and timing into resources as important as food itself. Vegetation could expand after wetter intervals, then retreat when dryness returned, repeatedly opening and closing corridors across the supercontinent. Such instability prevented many communities from settling into permanent arrangements, keeping competition fluid and ecological opportunities surprisingly temporary. A lineage thriving beside one river might disappear beyond the next dry basin, making geography a powerful filter on survival. This patchwork world rewarded mobility, efficient movement, and flexible feeding, traits that would later matter greatly to several archosaur groups. Still, no single trait explains success, because evolution works through combinations of anatomy, behavior, reproduction, environment, and plain historical chance. The Triassic therefore became a laboratory of survivors, with many reptile and synapsid lineages exploring different solutions to the same instability. Some grew armor, some became faster hunters, some returned toward water, and others refined teeth for increasingly specialized diets. Every experiment changed the neighbors around it, because predators shape prey behavior while herbivores reshape vegetation through feeding and movement. As ecosystems gained complexity, competition intensified, and surviving lineages faced opponents that had evolved under the same unforgiving conditions. Recovery was creating strength, but it was also creating rivalry, transforming empty ecological space into a crowded contest for resources. One branch of reptiles would become especially important in that contest, although its future winners were still far from obvious. Waterways preserved life during dry intervals, concentrating fish, amphibians, reptiles, and vegetation wherever rivers remained reliable enough to support them. Large amphibians still occupied important freshwater roles, reminding us that Triassic rivers were not simply reptile kingdoms from the beginning. Their broad heads and ambush habits suited murky margins, where prey approached shallow water and danger could remain almost invisible. Fish communities also recovered, supplying energy to larger predators and reconnecting aquatic food webs that catastrophe had severely disrupted. Along muddy banks, tracks recorded brief encounters between land and water, preserving behavior that bones alone could never reveal. Reptiles increasingly exploited these river systems, some hunting from shore while others developed bodies better suited for semi-aquatic life. The result was a layered ecosystem, with food moving from plants and small animals toward progressively larger consumers. Whenever drought shrank a river, that hierarchy compressed into fewer pools, intensifying competition among predators that normally kept greater distance. Floods reversed the pressure, spreading water across plains, reconnecting habitats, and allowing animals to disperse before isolated pools vanished. These alternating contractions and expansions repeatedly rearranged communities, turning rivers into both refuges and engines of evolutionary change. Freshwater edges also brought different lineages together, making them arenas where hunting styles, defenses, and locomotion could be tested. A successful river predator needed more than powerful jaws. Timing, camouflage, body control, and patience could matter just as much. Those pressures would eventually favor remarkable reptiles whose bodies resembled later crocodilians, despite belonging to distinctly different branches. Their arrival would make Triassic rivers look strangely familiar, even while the animals themselves belonged to a vanished evolutionary world. The water had become crowded again, and competition along its banks would soon reveal how far reptile diversification had progressed. Among the rising reptile groups were archosaurs, a broad lineage that would eventually include crocodilian lines, pterosaurs, and dinosaurs. Early archosaur relatives explored many body plans, from lightly built runners to heavily armored herbivores, and formidable terrestrial predators. Their diversity matters because dinosaur evolution happened inside this crowded radiation, not on an empty stage waiting for a champion. Different archosaurs divided habitats by size, diet, posture, and hunting style, creating overlapping networks of competition across Pangea. Some lineages evolved more upright limbs, placing their bodies differently over the legs and changing how efficiently they could move. Others relied on armor, mass, or ambush, proving there was no single Triassic formula for surviving the new terrestrial world. Predators at the top of these communities were often not dinosaurs, despite the later fame that makes dinosaurs dominate our imagination. That difference is crucial. Evolution does not know the future, so successful dinosaurs had to compete with equally real alternatives. Every encounter favored some combination of speed, endurance, senses, feeding anatomy, reproduction, or simple access to a better habitat. Success could also be temporary, because a lineage adapted to one climate regime might struggle when rainfall patterns shifted again. The Triassic therefore produced winners within winners, as broad successful groups repeatedly split into new ecological specialists. Archosaurs gained ground while synapsid survivors persisted beside them, keeping the future of terrestrial dominance genuinely undecided for millions of years. In that prolonged contest, dinosaurs first appeared as one experiment among many, not as rulers announced by some evolutionary destiny. Their earliest advantages must therefore be judged against the competitors surrounding them, rather than against the giants they would later become. To understand dinosaur success, we must first meet the animals already controlling the rivers, plains, and predator niches they entered. Phytosaurs prowled Triassic waterways with long snouts and armored bodies, filling crocodile-like roles while belonging to a different archosaur branch. Their resemblance to crocodilians shows how similar ecological problems can repeatedly shape unrelated bodies toward familiar-looking solutions over deep time. On land, armored aetosaurs browsed vegetation while large predatory archosaurs occupied roles that later generations might instinctively assign to dinosaurs. Synapsid survivors remained important too, including cynodont relatives whose descendants would eventually contribute to the mammalian story far later. This mixture made Triassic ecosystems evolutionary mosaics, combining ancient survivors with newer lineages that were only beginning to diversify. No viewer standing there could have identified the future winners simply by choosing the largest predator or most armored herbivore. Many apparently successful groups would vanish before the Jurassic, while smaller competitors would inherit opportunities created by later environmental upheaval. Dinosaurs at this stage were generally modest components of communities, sharing space with predators and herbivores that often seemed more imposing. That modest beginning makes their later dominance more revealing, because it forces us to search for processes rather than destiny. Competition can favor efficiency without producing immediate conquest. A lineage may persist quietly until environmental change alters the rules. Dinosaurs could therefore accumulate useful traits while remaining secondary players, surviving long enough for future opportunities to appear. Their rivals were not evolutionary failures. Many were exquisitely adapted to Triassic conditions and successful across enormous geographic ranges. That success made every dinosaur expansion a real contest for food, territory, breeding space, and access to seasonal water. The balance could shift locally without changing globally, so different regions of Pangea likely told different versions of the same story. Fossilized footprints preserve that uncertainty beautifully. Small tracks cross sediments, once dominated by animals whose names most people never learn. Fossil evidence suggests true dinosaurs emerged during the Triassic, evolving within archosaur communities already crowded with capable competitors. The earliest known forms were comparatively small, lightly built animals, far removed from the colossal silhouettes that later defined dinosaur fame. Many early dinosaurs moved on two legs, giving their forelimbs freedom while powerful hind limbs carried the body across open ground. Bipedal movement was not uniquely dinosaurian, yet it became part of a flexible anatomical package that several early dinosaurs exploited. Light frames may have aided rapid movement, useful for chasing small prey, escaping larger predators, or crossing exposed terrain. Carnivorous early forms carried grasping hands and sharp teeth, while other dinosaur lineages soon explored different feeding strategies. Names such as Eoraptor and Herrerasaurus come from later Triassic rocks, offering glimpses of how varied early dinosaurs already were. Their fossils do not reveal a single birthplace with certainty, because the earliest dinosaur record remains incomplete and geographically uneven. That incompleteness matters whenever we describe beginnings. The oldest fossil found is not necessarily the first member that ever lived. Paleontologists therefore reconstruct dinosaur origins from bones, tracks, anatomy, rock layers, and evolutionary relationships rather than one perfect fossil. The resulting picture is gradual. Dinosaurs appeared, diversified, and spread while many neighboring reptile groups continued thriving beside them. Early success may have depended on being versatile enough to exploit openings without requiring complete control of any ecosystem. That strategy favors persistence, because a lineage can remain present through difficult intervals until circumstances suddenly reward its existing abilities. Dinosaurs were becoming evolutionary options with staying power, but staying power alone still did not make them dominant across Pangea. The deeper puzzle is why these modest animals endured long enough for later crises to remove competitors that once overshadowed them. Dinosaur evolution was constrained by the same forces affecting everyone else: climate, food availability, geography, predators, disease, and reproductive success. In some habitats, established competitors already occupied profitable niches, leaving newcomers to survive along ecological margins or exploit narrower opportunities. Predatory archosaurs could challenge small dinosaurs directly, while large herbivores controlled access to vegetation and altered landscapes through feeding. Geographic barriers mattered too, even on a supercontinent, because mountains, deserts, latitude, and seasonal water could separate populations. Separated populations evolve under different pressures, so dinosaur communities could diverge regionally long before their descendants became globally familiar. Climate belts also shaped vegetation, which determined where herbivores could feed and where carnivores could reliably find concentrations of prey. A fast runner gains little if heat prevents activity, food disappears, or breeding sites fail before the next generation survives. This is why evolutionary advantages should be treated as conditional tools, valuable only when environments make those tools useful. Dinosaurs possessed no guaranteed path forward, and several other reptile groups remained successful for much of the Triassic. Their eventual rise therefore demands a sequence of events, not a single magical adaptation that suddenly transformed losers into rulers. First came survival after the Great Dying, then diversification, then repeated environmental disturbances that kept reopening ecological possibilities. Each disturbance could eliminate local competitors, alter vegetation, redirect rivers, or favor migrants already equipped to exploit changed conditions. Over long timescales, those temporary advantages can accumulate, turning marginal lineages into widespread ones without any single decisive moment. The Triassic story is therefore less a coronation than a tournament repeatedly interrupted by changing climate and ecological collapse. One especially important climate disturbance would soon reshape habitats again, accelerating changes already underway within dinosaur and competitor communities. Later in the Triassic, the Carnian pluvial episode marks an interval when rainfall patterns changed dramatically across many regions. The event was not simply endless rain everywhere, but a broader climatic disruption recorded differently across ancient environments. Wetter phases could expand rivers and vegetation, while changing runoff and sediment transformed the habitats surrounding recovering terrestrial communities. For herbivores, altered plant communities meant new foods and new challenges, forcing digestive strategies and migration patterns to adjust. Carnivores followed those shifts indirectly, tracking where prey gathered and abandoning territories that no longer supported dependable hunting. Dinosaurs already present within these systems could expand where opportunities opened, especially if competitors declined or habitats reorganized. Fossil patterns suggest dinosaur diversification accelerated during parts of the later Triassic, though causes remain more complex than rainfall alone. Climate interacts with volcanism, geography, vegetation, and competition, so no single trigger can explain every dinosaur expansion across Pangea. Still, disturbance creates ecological openings, and lineages already experimenting with locomotion and feeding can sometimes exploit them quickly. This is the recurring Triassic pattern. Catastrophe does not design winners, but it repeatedly changes the contest they must survive. As habitats shifted, Some dinosaur populations spread into regions where earlier barriers of climate or competition had restricted them. Isolation could then produce differences between populations, while renewed connections allowed successful forms to disperse across larger areas over generations. That cycle increased ecological variety, helping dinosaurs occupy more feeding roles and body sizes than before. Their rise was becoming visible. Yet formidable non-dinosaur archosaurs still controlled major niches and remained serious competitors across Pangea. The next transformation would come from diversification itself, as dinosaur lineages split into increasingly distinct ecological strategies through time. Predatory dinosaurs refined lightweight bodies, grasping limbs and cutting teeth, while herbivorous relatives increasingly specialized for processing plants. Early sauropodomorphs began exploring larger body sizes and long-necked feeding strategies that would later produce the giants of Jurassic landscapes. Small predatory forms occupied different spaces, pursuing insects and vertebrates that larger hunters might ignore or struggle to catch. Other early dinosaur groups experimented with herbivory, although their earliest fossil record remains patchy and sometimes difficult to interpret. Diversification reduced direct competition within dinosaurs by allowing different species to exploit different foods, habitats, and times of activity. It also made dinosaur communities more resilient, because ecological failure in one niche did not automatically eliminate every dinosaur lineage. Body size itself became another axis of specialization, influencing diet, movement, predator risk, reproduction, and access to vegetation. Larger herbivores could reach different plants and process more food, while smaller animals remained agile within denser cover. Predators responded to these changes, creating evolutionary feedback between prey defenses, prey movement, hunting anatomy, and sensory abilities. No lineage evolved alone. Every successful adaptation altered selective pressure on neighbors, sharing the same landscape and resources. Dinosaurs were therefore becoming part of increasingly intricate food webs, not merely replacing old animals one species at a time. This complexity gave them more ecological footholds, making complete elimination less likely when local conditions turned unfavorable again. At the same time, their competitors continued evolving, ensuring that dinosaur expansion remained contested rather than inevitable across Pangea. By later Triassic time, dinosaurs occupied more roles and regions, yet the old competitive order had not disappeared. A supercontinent could spread successful lineages widely, but its enormous scale also created climates and barriers that kept communities distinct. Pangea connected vast stretches of land, allowing animals to disperse without crossing the wide oceans separating today's continents. That connectivity could turn successful adaptations into continental expansions, especially along river systems and climatically favorable corridors for migration. Yet, a connected continent was not uniform, because latitude, elevation, rainfall, and distance from coasts produced sharply different environments. Some regions supported greener floodplains, while others remained seasonally harsh, forcing animals to migrate, specialize, or disappear locally. High-latitude communities experienced different daylight cycles and seasonal pressures than populations nearer the equator, shaping distinct ecological rhythms. Deserts could separate populations just as effectively as seas, especially when reliable water existed only along distant river corridors. Isolation encourages divergence, allowing populations of related animals to accumulate differences under separate environmental pressures over many generations. When corridors reopened, those differentiated populations could meet again, compete directly, or spread into territories abandoned by others. This repeated separation and reconnection helped make Pangea both a highway for dispersal and a machine for diversification. Dinosaurs benefited from that geography when conditions favored them, but competitors could use the same corridors just as effectively. The contest therefore unfolded region by region, with local extinctions and expansions gradually changing the continental balance through time. And a lineage could be dominant in one basin, rare in another, and completely absent beyond a climatic barrier. This geographic complexity cautions against telling one universal Triassic story, because fossil assemblages preserve only fragments of a vast world. Still, Across those fragments, dinosaurs appear increasingly diverse and widespread as the Triassic advances toward its final crisis. Geography had given them roots to spread. The coming upheaval would determine which travelers remained when those roots changed again. By this stage, Triassic food webs linked plants, insects, small vertebrates, large herbivores, and multiple tiers of predators. Herbivores shaped vegetation through selective feeding and movement, while their droppings and remains returned nutrients to soils and waterways. Predators influenced where prey gathered and when they moved, creating landscapes of risk that altered behavior even without a chase. Scavengers and decomposers completed the cycle, breaking organic material down and releasing nutrients that plants could use again. This web-like structure made mature ecosystems productive, but it also created dependencies that could amplify disruption when key connections failed. Cynodonts, archosaurs, amphibians, and dinosaurs shared these networks, each lineage carrying a different history from the extinction's aftermath. Their coexistence proves recovery was not a simple replacement of Permian animals by dinosaurs, but a long ecological negotiation. Plants mattered just as much as predators, because shifts in vegetation could reorganize entire communities from herbivores upward. Seed plants and ferns occupied different habitats, creating mosaics of cover, browse, nesting sites, and shade across floodplains. Small animals exploited those mosaics too, filling niches invisible beside giant reptiles but essential for transferring energy through ecosystems. As ecological complexity increased, dinosaurs gained more opportunities to specialize, while established competitors became vulnerable if their preferred resources changed. The same richness that signaled recovery could therefore create new fragility, because specialized species depend on particular combinations of conditions. Late Triassic ecosystems were no longer the sparse survivor worlds of the beginning. They had rebuilt complexity and competition. That achievement makes what happened next more dramatic, because another extinction would strike a world that had spent millions of years recovering. This time, dinosaurs would enter the crisis not as newcomers, but as diversified survivors spread across many ecological roles. Near the Triassic's end, Pangea began rifting more dramatically as the future Atlantic region opened along enormous fractures. Vast volcanic provinces accompanied that tectonic upheaval, releasing lava and gases across episodes that transformed climate and environments. The Central Atlantic Magmatic Province is strongly associated with the Triassic-Jurassic extinction, though its environmental effects unfolded through complex pathways. Carbon dioxide released by volcanism could intensify greenhouse warming, while other emissions caused shorter disruptions with very different consequences. Rapid environmental swings are especially dangerous for specialized species, because adaptations tuned to stable conditions can become liabilities quickly. Food webs begin failing when plants, herbivores, and predators respond at different speeds, breaking connections that once supported entire communities. Some animals migrate toward tolerable climates, others persist in refuges, and many disappear when suitable habitats contract beyond recovery. Phytosaurs and several other prominent Triassic reptile groups vanished around this transition, removing competitors from major ecological roles. Their disappearance did not prove dinosaurs were inherently superior. It changed the ecological landscape in ways surviving dinosaurs could exploit. Survival itself may have depended on geography, body size, diet, physiology, and sheer luck interacting differently among lineages. Extinction removes branches without consulting future potential, so history can redirect evolution by eliminating competitors rather than inventing new adaptations. For dinosaurs already diversified across several roles, surviving this crisis meant encountering a world with dramatically altered competitive structure. Rivers, forests, and plains remained, but many familiar inhabitants were gone, leaving ecological vacancies across land communities afterward. Those vacancies were opportunities only for survivors capable of reaching them, reproducing successfully, and functioning under the new conditions. The second great reset of the early Mesozoic was opening, and dinosaurs entered it far better positioned than before. The answer to our thesis is therefore not one secret adaptation, but a long sequence of survival, diversification, and ecological opportunity. The great dying shattered older ecosystems, creating the unstable world in which Triassic survivors had to rebuild from reduced foundations. Within that recovery, archosaurs diversified, dinosaurs emerged among them, and competition tested which lineages could persist across changing environments. Climate disruptions repeatedly rearranged habitats, sometimes hurting dinosaurs, sometimes helping them, and constantly altering which ecological strategies paid off. Dinosaurs survived long enough to diversify before the Triassic ended, so the final crisis encountered a lineage already spread across roles. When major competitors disappeared, those existing dinosaur lineages could expand into spaces that evolution had not specifically prepared for them. This is the central irony. Catastrophe created openings, but only previous survival and diversification allowed dinosaurs to capitalize upon them. The biggest extinction in the story did not crown dinosaurs. It dismantled an old order and made later opportunities possible. Millions of years of competition then shaped dinosaurs inside that open world, filtering lineages through climate shifts and ecological rivalry. A second extinction removed additional competitors, turning persistence into expansion and setting the stage for Jurassic dinosaur dominance. Seen this way, dinosaur success becomes less mysterious and more profound. Because it depended on contingency as much as capability, evolution produced many capable Triassic animals. Yet history repeatedly changed which capabilities mattered, rewarding survivors under newly altered conditions. Dinosaurs were neither inevitable conquerors nor accidental passengers. They were adaptable participants whose opportunities expanded when ecosystems repeatedly reset. Their rise, therefore, belongs to the entire Triassic recovery, from sparse survivor communities to complex food webs and final disruption. Only after following that whole journey can the first dinosaur age be understood as an inheritance purchased through survival. As the Jurassic began, dinosaur communities expanded into ecological roles left open by vanished rivals, changing terrestrial landscapes on a continental scale. Large herbivorous dinosaurs became increasingly important, while predatory dinosaurs diversified alongside them, building food webs unlike those of early Triassic recovery. The Age of Giants came later, but its foundations were laid by small survivors navigating unstable ecosystems millions of years earlier. That history changes what dinosaur dominance means. It was not a sudden conquest, but the delayed outcome of repeated ecological turnovers. Each extinction erased possibilities as well as competitors, leaving descendants to build futures from whatever biological tools remained. The Triassic reminds us that recovery can be creative without being gentle, generating new worlds through relentless pressure and loss. Long after those animals vanished, rock still preserves their bones, burrows, river sediments, and volcanic layers as fragments of one transformation. A small fossilized footprint can cross one slab today, echoing the uncertain traveler that once moved through a world of larger rivals. That trace survives because chance favored preservation, just as chance sometimes favored the lineages whose descendants continued into later ages. Modern birds carry the dinosaur story forward, living evidence that one dinosaur branch survived far beyond the Mesozoic world. Their existence turns the Triassic from remote history into ancestry, connecting ancient experiments in survival with animals still around us. The dinosaurs did not inherit a healthy planet. They inherited openings created by catastrophe, then survived long enough to transform them. Which Triassic survivor surprised you most? And which lost branch would you want to see explored in a future Aeon Earth documentary? If this journey changed how you see dinosaur origins, share it with someone who still imagines their rise as inevitable. Subscribe to Aeon Earth for the next deep time journey, where another vanished world will reveal how fragile dominance can be.